So this video is on the first of two videos on the topic of 1.4 image encoding. I'm going to break this into two, so in case I mess it up, I don't have to redo it all of it. So this is the outline for this stack of slides. They're updated. They're on the website by now. So really, I'm going to talk about the three important aspects to image encoding for most of the imaging that we do, which is slice selection, frequency encoding, and phase encoding. And I'm going to break this in two. So getting up to slice selection, I'm going to talk first about band selective pulses, and then a little bit about what gradients are, then slice selection and the gradient echo experiment. And I'll stop this video then, and we'll do frequency and phase encoding in the subsequent last video for this section. Okay. So let's start with thinking of this picture right here. Imagine a magnetization M of an isochromat that's on resonance, and I'm trying to excite it. I'm trying to flip it down from its equilibrium state here down into the transverse plane from, let's see, that's x, y, z, from the z-axis to the y-axis. So what you do is if you turn on a B1 pulse like this along the x-axis, M will rotate down at a constant velocity, and I'll turn it off when it gets to that axis. So that works fine if it's on resonance, because that will stay still because that's perfectly on resonance, and the B1 will just be this, and there's no off resonance, so that you get a nice perfect rotation. If you're a little bit off resonance, though, it doesn't work as well. And what happens is as we talked about before, the effective magnetization in the rotating frame is the linear combination of your applied B1 field and whatever off resonance term we pick for whatever that isochromat is, what frequency it's at. So instead of rotating about this vector, the B1 vector, it's rotating around B1 effective. And so M, instead of going straight down in the YZ plane to here, it rotates a little bit and comes a little bit into the plane. So there's a little bit of MZ left. It's not all MXY. It's the MXY magnitude is a little smaller, and it's got a little phase component to it too. So this is what's happening if I put on a square RF pulse, and this is the effect of the magnetization for different off-resonance values. And that's what I'm plotting down here. This is the magnitude of MXY, which is really that shadow, the length of that shadow in the XY plane there, as a function of off-resonance frequency, and this is that large omega. So this is on resonance, we get a nice excitation. So here I'm trying to do a 90-degree excitation, and on resonance I'm able to achieve that. Off resonance, I don't quite get that. And as you get off resonance, you have this oscillating behavior, and you can maybe imagine what's happening as those off resonances get bigger, that you're getting multiple rotations there. So this is a little insight to what happens and why we have to look at off resonance and why we get not quite the response you're expecting if you're not on resonance. Typically, if you look at the response, if you're trying to do 90-degree excitation, you would say this is the output. The output you're trying to produce is an MXY, and the full width half max of this excitation is the half height, so 0.5, and the width in hertz, which in this case looks like maybe 1 kilohertz full width half max. So this example, let's see. So this is a common thing. If you wanted to try a different RF pulse, for example, you would look at simulate the response that you'd get for different off-resonance values like this. You might recognize this, by the way, as the input function is a square, so that's a rect function, and the output you might recognize is the magnitude of a sinc function. And these happen to be, it's not happen to be, but these two are approximately Fourier transform pairs. Well, a sinc function is a Fourier transform of a rect function, and this looks like the absolute value of a rect function. It turns out that it's not exactly the Fourier transform of a rect function. If you pick a very small flip angle, say something like, under, what do I say here, 30 degrees or so, the Fourier transform of a rect is a very good approximation to what you get. So this is the Fourier transform of a rect, and this is the block simulation of the MXY you would get for a 90-degree excitation pulse. It's pretty good. It's a pretty good approximation. The frequency, the nulls there are at the same points. It's a little broader up top. But if I looked at the response for a 10-degree pulse, you would find these two to be in very good agreement. So this is very insightful, and this has driven a lot of the design of RF pulses, is noting that the frequency response, in other words, the MXY, can be well approximated by the Fourier transform of the RF pulse shape. So in a lot of applications, what we really want is we want to produce a rect. We want a band-limited excitation where we excite everything within a band and nothing outside of a band. So we'd like a perfect band square response. And using the same concept that you have an approximate Fourier transform relationship, people looked at the inverse Fourier transform of a rect, which is a sync. So in fact, if you play a sync pulse like this, you get something that's much closer to a rect than you would get if you played a rect pulse up there. So this is the basis behind doing band-limited excitation, and the idea of why sync pulses are commonly used because of the Fourier transform relationship between sinks and rects. And sync, I didn't define it before. The sync of x is basically the sine of x over x. You have to scale it in order to get that to work quite right. I want to point out that when we say sync, we usually mean truncated sync, because a sync is defined all the way out to infinity in both directions. But we never play pulses for an infinite amount of time. We don't have that kind of time. So they're always going to be finite limited. So we always truncate them off somewhere. And that truncation, actually, in the RF pulses is what causes this ringingness, which makes them imperfect. If you make a longer pulse, so there's less truncation, you can see that the ringing effects are decreased. And that's the example here with this longer sync pulse, or this, not necessarily longer, but more shaped sync pulse up here. Less truncated sync pulse, I should say there too. By the way, when I describe sync pulses, and a lot of people do, refer to this as a 3-lobe sync, 1, 2, 3, and this is a 7, 1, 2, 3, 4, 5, 6, 7. Some people look at on the sides and they would call that, I guess, 1, 2, 3-lobe sync. There's really not a definition. I think the definition I use is more common. That's why I use it. But you'll see some people describe that differently. I just want to point that one out. So that's the idea behind band-limited pulses. So you have a shaped pulse, here is sync function, to try to excite just a narrow band of frequencies and not excite stuff outside. So Dr. Garwood's lectures in the next few classes are going to talk more about that. And your second homework is really going to be taking a sync function and simulating this response as a different offsets, as well as some variations on that. So you look at homework 2, which you should be able to get to after just this set of lectures. Take a look at that. There's a lot of different pulses that you can use here that we're not going to get into, and maybe Mike will cover a little more in the next section. So that's band-limited excitation. Before we talk about slice selection, I want to cover gradients and what they do and why. So when we talked about the FID experiment, the free induction decay, we just put a sample in the middle of an RF scanner. All we had is a big solenoid that produced a big B0 uniform field in the Z direction, we call B0. And we put our sample here in the center. Now we're going to add another component, which is what we call gradients. And the idea behind a gradient is, let's look at the Z gradient here first. And that's, look at this drawing over here with this set of Z gradients. So what these are two simple loop coils. I'm showing them conceptually as simple loops. They're usually comprised in practice of more than the simple loops to improve their performance. But you can think of them as a simple loop coil here. And they're aligned like offset this direction relative to the B0. So in this drawing of the scanner, there's one closer to you and one further away, and they're symmetric about the center of the scanner. So think about for a sec, you normally have a big B0 field that's aligned horizontally like this. This current in this loop will produce an increased field, an additional small B field aligned with B0 at this point in space. And this loop, with the current going the other way, is going to produce one that's opposing that external B field. And if you were going for points between these two loops, you would see that the two effects combine linearly, and at some point they cancel perfectly. So right in the middle of the scanner, if you run current in this sort of opposite directions in these two loops, you'll get no effect at the center, but increased field here and decreased field here. And what you're trying to do with this is make a plot like this. So this is a plot of the B0 field strength as a function of space. And if you get in the middle part of it here, you get a very linear behavior. And that's really what gradients are designed to do, is to produce a linear variation of the B0 field as a function of space. And this is the Z term. So as we mentioned before, Z is always going along the axis of the scanner. Y is usually, if you're laying down, it's in the anterior-posterior direction, and X is right-left. Scanners can be flipped, so X could be left-right, but this is the most common way to look at So a z gradient is one where you put currents on, you make a linear field in the z direction like this. A negative z gradient would have that go the opposite direction. You can make the same sort of behavior, almost the same linearity. The performance is not quite as good, but with x and y gradients. And these look a little more complicated. So this is a set of, as I'm showing them here, these are y gradients. So putting current on these pairs, so there's 4 elements, will produce fields either that are in the y direction. Here in the positive y direction, you get a field that's opposing the B0 field. So the B0 field is weaker here and stronger down there. So these set of coils make it in that simple direction. And you can imagine a rotated set of these that will do it in the x direction through the plane here. So this is actually a y set that I'm showing you here. So it's important to note that these are, when I put on the z gradient here, what I'm trying to do is increase B0, the z component, and decrease the z component as a function of space. I'm not trying to, these coils, if implemented correctly, do not cause an x component or a y component. They're just adding to subtracting the z component of the field as a function of space. Same thing with the x's and y's. All they're doing is trying to add the b to increase or decrease the B0 component, and they don't cause x or y components to the actual the B fields. That's not entirely true. I say here gradient coils produce negligible B fields in x and y directions. They do cause a little bit, but those are relatively small, and those are called concomitant gradients that at 3T and above we mostly ignore, but they can be in effect in subtle cases at 1.5 or lower fields. Also, if you, in a scanner, you typically have a set of x, y, and z gradients. And even though they're overlapping in space, they act orthogonally. So if I put a z gradient on, it will produce the z gradient shape you see here without affecting the y, the variation of the B0 field in the y direction or the x direction. So they're orthogonal. And that's the idea behind them. Again, that's not perfectly true. You have to design these gradients very carefully for that, and they do some tricks to help make that be as orthogonal as possible. But from a sequence perspective, we can treat them as being orthogonal. I also want to point out that as we switch these currents, and with gradients, we do switch them quite frequently. We switch them on and off with like roughly a millisecond time frame. So that gives you switching frequencies in the sort of kilohertz range, 1,000 hertz range. And so this really doesn't interfere with the B1 field much, because those are at higher frequencies. The B1 fields are at megahertz frequencies. So in some respects you can think that, well, they're just at different frequency ranges, so they don't really interact very much. But the whole reason I'm talking about gradients is they're important for everything else in this stack of slides. This is how we do image encoding because of plots like this. By setting up a linear gradient offset, then the Larmor frequency at this point in space is going to be higher than the frequency at this point in space. And if the little isochromats here in this guy's stomach are at higher frequency than down in his upper leg, shall we say, then we can decompose those signals. We can treat them differently because of their frequency. And it's because this Larmor frequency is proportional to the magnetic field is the key to image encoding. So, considering gradient coils and what we just talked about in terms of slice band selective excitation with RF pulses, we'll come to the first piece of imaging, which is slice selective excitation. So I like this plot here, and by the way, I do a lot of work in breast imaging, so that's where this slide came from. Suppose this is a cross section of a subject laying on their back in the scanner, and I want to select a slice through this point in space. But first, think about how I do that. First thing I do is I turn a gradient on. And I'm going to turn an x gradient on, such that this is a plot of the z field, the z component of the magnetic field, and this line represents my gradient. So when I turn the gradient on, this is the equation for it. The magnitude of the gradient is gx. At the center of the scan, at x equals 0, there is no effect. This is 3 Tesla. The field there is 3 Tesla, and the frequency is gamma times 3 Tesla, which is whatever, 128 megahertz. So when I put that gradient on, it doesn't affect the center at all, but it makes the samples over here, the part of the body here, resonate at a higher frequency than the parts in the side of the breast, which are going to resonate at a lower frequency. So imagine I have the subject in, I turn that gradient on, so the Larmor frequencies are different through the body, and then I play out a band selective RF pulse. This is the response profile I'm trying, you have to tilt your head sideways maybe. If you go back 2 slides and look at these, that's what I'm doing here. I'm playing out a pulse like a sync here in this direction here. So I play a band limited RF pulse, and let's imagine it was, if you just use your imagination, like it was a pretty good selection, so everything inside there is excited and everything outside is not excited. You look at what frequencies it'll excite. That corresponds to these points in space by looking at this curve, and it effectively excites this slice of tissue and doesn't excite the stuff on the outside. So this is slice selection. If I want to excite that slice, I play that pulse with that gradient on at the same time, and I get these, and everything outside doesn't see any effect at all, which is still pretty amazing to me. So a few comments about it. So we refer to this thickness here, the slice thickness, and its relationship to the bandwidth of the RF pulse is described here. The thickness is proportional to the bandwidth, and it depends on the gradient strength. We often use, in characterizing RF pulses, the bandwidth time product, or I think we say bandwidth time product. Here at the CMRR, and I think Mike he started doing this, calling this R's. So a lot of people here refer to it as the R value of a pulse. I really don't know how much people do that outside of CMRR, but we do that here. You'll see officially the more accurate term, bandwidth time product, or the more descriptive term at least. But also keep in mind, so a couple other comments about this. These pulses aren't perfect. So the slice selection profile isn't a perfect direct. The RF excitation profile isn't a perfect direct. So the slice selection isn't a perfect direct either. It's not exactly in and exactly out. It's got some errors. There's a little signal from either side that's getting excited, and there's some stuff inside that's not getting a full excitation, as you can see there here. But this is the ideal case. We're trying to really get a perfect slice that way. So looking at a plot like this, and there's a lot in this plot, I think, but you can start imagining how you do different types of slice excitations. For example, if I wanted to not excite this slice, but excite one over here, all I would do is I would apply this RF pulse at a different frequency. I would shift the transmit frequency. That's what TOF is, transmit offset frequency. That's a nomenclature from the Agilent systems, but just the transmit frequency. If I were actually broadcasting that pulse at a slightly different frequency here, that same slice would be excited for more laterally in this case. Likewise, if I wanted to excite a medial slice, I would shift that frequency down, and then I would excite a slice here in the middle of the breast. If I wanted to excite a thinner slice, there's a couple ways of doing it. One is to have a pulse with a narrower bandwidth here, and then that would obviously correspond to a thinner slice here. Another thing is to do a steeper gradient. Now, if I made this gradient steeper, a stronger gradient, so this line goes vertically, I would also have to adjust the transmit offset to get it in the same position, but you can calculate that. But a steeper gradient will give you a narrower slice in general. And you calculate the offsets very easily from these equations here like this. So this is the general idea for slice excitation. A combination of the transmit offset, the transmit frequency tells you the position of the slice, and the bandwidth of the RF and the gradient together determine the slice thickness. A couple other comments I want to make about slice selection. This is what it looks like in a practical sequence. You play a shaped RF pulse like this while you have a slice select gradient on. And very commonly we have we'll use a slice refocusing gradient like this. So we call this a slice selection rephasing lobe. And the reason we do this is because for a lot of the stuff I'm talking about, we're going to ignore effects that happen during the RF pulse. But during the second, I mean, these are typically a couple milliseconds, say 1 to 4 milliseconds long for excitation. 4 would be kind of long. 2 milliseconds is reasonable. But there's dephasing. There is dephasing during this part due to that gradient being on there, and we need to correct that. And this lobe here ends up correcting it. It's important when you're doing gradient dephasing to have the area of the gradient dephasing lobe to be 50%, or it's going to be match the second half of that RF pulse there. If you had a more complicated RF pulse, like something that's asymmetric, for example, which you can do, you might need to experimentally or numerically calculate what the area ratio is to cause complete dephasing, because as you'll see in a second, this gradient will cause some spread out of the frequency, and this just corrects that amount. I also want to point out that we can apply these in any different direction. So this is what we just showed you. This is an RF pulse applied in the X direction. So that was my example in the breast where we're doing an X excitation. But we could play that same RF pulse and move those gradients down to the Y, and we'll do a Y excitation, or down to I don't know why, that should be a Z, not a P, to the Z-axis and do a Z excitation. But if you play a pulse on multiple gradients at one time, like I'm showing you here, you don't get an X. If you played an X and a Y, you don't get an X slice and a Y slice. You get an oblique slice. So you combine these gradients together and you can calculate the net gradient. There's really only one gradient when you combine them together, and then the slice is perpendicular to that one. Just like if you put on an X gradient, you get a slice that's perpendicular to the X. I'll go back and show you that. An X gradient gives you a slice perpendicular to X. If you put on X and Y, you'd get a slice that's perpendicular to X and Y, so it'd be a diagonal through there like that. That's what I'm showing you here. So you can pick an arbitrary orientation of a slice by playing out multiple gradients like this, and you have to calculate them together. Typically though, when we do RF pulse sequences, we'll often just refer, here I'm showing you the magnet X, Y, and Z coordinates. We'll often design pulse sequences in a logical space where we have slice selection being one axis and the other two axes we'll call phase and readout, as I'll get to in a little bit. So when you're looking at pulse sequences, this is a little tip. There's two things that are relatively common. One is this example where we have a hard pulse, which in general excites a broad band, a non-selective band, and there's no gradient on. So if you do something like this, you're really trying to excite the entire object, no spatial or frequency selectivity. This is what you expect to see in a slice selection, a shaped RF pulse with a gradient underneath it and typically a rephasing lobe to correct it. So this is slice selection, this is excite the whole object. There are other purposes of this. If you had no gradient on and you play a frequency selective excitation, this can be useful for selecting different chemical species, which you'll hear about later, like exciting water or exciting fat and then suppressing it. So that's frequency selective excitation. And this, for example, if you did a hard pulse with a gradient on it, you get kind of a crummy RF pulse, because if you remember, the profile of the sync of a rect pulse is kind of a crummy looking sync with a poorly defined bandwidth. So you typically don't do something like this. But when you're looking at pulse sequences, this is just a little tip for being able to identify what we're trying to do with the different the different gradients in RF pulses. Okay, let's talk about the gradient echo experiment. So, sorry, I'm losing my voice a little, trying to drink some tea here. This is the next, another basic experiment, which looks a lot like the FID. We have a 90-degree excitation, we wait a little bit, and then we measure turn on our ADC and measure our sample at this point in time. But instead of sampling right here, as soon as we put on the 90-degree pulse, we turn on a gradient. So if you think about what happens here, and we'll get into this in a little more detail on the next slide, that gradient is going to cause all the isochromats that vary in space to have very different frequencies and very different phase. And all those phases are going to cause cancellation of the signal, and the frequency and all the coherence is going to decrease very rapidly with this gradient on. And so if you were to actually measure the signal at that's coming into your coil, which you don't typically turn on the sampler until later, you would see that that signal would decay very quickly because of that gradient on there. The gradient, unlike T2 star, is reversible. So you put the gradient and the X direction on and turn it off for the same amount of time. These two areas will cancel out, and all that dephasing caused by this gradient lobe is undone by this gradient lobe, and you're back to as if there was no, at this point in time, you would not know if those gradients had ever been on. And so you go back to exactly what you would get from an FID, which would have been this envelope of T2 star decay. So if I were to set all these gradients to 0, you would get you would just get regular T2 star decay, and we have basically the FID experiment. Putting this gradient on knocks that signal way down, and then sets it to 0 and has it refocus back here and cause this echo to appear, which is the gradient echo. Let me just go into this in a little more detail on the next couple of slides. So this is using sort of this phase tracking, like we did a little bit in the spin echo, to understand what's happening with gradient echoes as well. And in this case, we're going to take a subject here, this happy subject, and their right arm is this purple line A, the center of them is B, and their left arm is the red line C. And we're going to assume here, we're going to ignore, well, mostly ignore T2 star. If everything was perfectly without gradients, everything's exactly at the flat magnetic field, we'll just ignore those effects, although I do have them drawn in down there a little bit. So let's look at this RF pulse here. So this plot here is the phase as a function of position. And we're only going to look at those three isochromats, A, B, and C. So here's the phase, and here's during the RF pulse. So we got my 90-degree excitation. Up until then, we'll assume that everything's, well, there's no phase because there's nothing in the transverse plane. And after I excite it, since it's perfectly uniform right here, they stay in the transverse plane. They don't accumulate or decrease any phase because I'm pretending there's no inhomogeneity between them. So ignore that T2 star decay down there. Imagine that's infinite. So there's no dephasing between them. Then when I turn the gradient on, you notice that the phase accumulates here for isochromat A and decreases for isochromat C. And this is the phase, notice the minus sign, which is why A is negative here and they flip around a little bit. But while these gradients are on, this has a linear slope which is dependent on the gradient magnitude and dependent on the position in space. So it's proportional to that value right there. So this accumulates phase. Then when I turn the gradients off, they maintain zero phase because we don't have any dephasing. And then when I flip the gradients the other way, the gradients go back down. And the slope of this is proportional to the amplitude of the gradient, so it's a little slower than when I had two stacked up. But you'll see when these areas balance out, I got 2 units here and 2 units here, this goes right back to 0. And at this point, now I have this destructive interference. Think about the T2 star plots. When the phases come back to 0, then I have coherence and an echo forms, and that is the gradient echo. So you get a gradient echo when these areas balance out, and the dephasing caused by these guys is canceled by the rephasing or refocusing by these guys, and poof, I got a gradient echo. Just like with other echoes, I can repeat it. So if I kept this gradient on here, I would cause more dephasing, which you see in these plots here, going in the other direction. And then this gradient lobe rephases them back, and I have another echo occurring here. So this is a multi-echo gradient echo with one occurring at this time point, one at this time point, and this duration is called, from the beginning of that 90-degree excitation to that point is the echo time. That's the TE. And this would be TE2, which would be that echo time here. So TE2 would be from this point all the way back to the middle of that 90. I'm showing it at the end of the 90, that gets to be a little a fine point, whether it's in the beginning or the end of the 90. Let's just say it's from the middle of the 90 is probably more correct. So you can do multiple gradient echoes, and this phase tracking is one way of looking at it. One way to think about too, so this plot underneath it I'm calling K, and this, by the way, is the K and K space, which I'll be explaining more as we go along. But K, well, I'll define it later. K really describes the state of these objects, kind of in that of all these isochromats in the x direction. So the Kx describes how spread out the phases are across the object. And that's sort of what's represented here. They're dephased a lot here, and at K0, the spread of phase in the x direction is nothing. When you have negative Ks, the spread is inverse related to the gradient, whereas and the magnitude is proportional there too. Maybe that'll be made a little clearer later, but you might want to come back to this little plot as we get going. As you can see from the last plot, the gradient-induced phase is reversible. So that what the gradients are doing is, if you think of a single isochromat, before a gradient, if you had 0 phase, if you turn the gradient on for a certain amount of time, you will add a certain amount of phase, and that phase is basically this K. It's the integral over time of that gradient magnitude. So actually, let me just jump to the next. Wait, I'm missing some slides. There we go, came back. So if you have a hard gradient set like this, so I have a fixed gradient with a magnitude of gx and a time of tau, the K value you get if you do that integral, I'll go back to this side real quick. Here's the integral. If gx is constant during that period, it pops right out, and then you get gx times tau is the magnitude of the K vector. So K essentially is the area of that gradient, and if you have a complicated shape, it's still the area of that gradient. So that's really what we're getting when we put on these gradients. They accumulate phase, and there's 2 ways of thinking about it. First, let me just look at these equations here. So when we apply a gradient, it is the gradient or the del operator of the BZ in space. You can describe it as the partial derivative like this of the Z field. In general, the total B field is a combination of the gradient field and the external B0 field in the z direction. Notice there's no x, y, or z components there. It's the partials in those directions. So the z field, the B field in the z direction is the default field here plus the gradient magnitudes times each of the positions in the space. That's what we're showing here. And there's two things you can think about this. As I mentioned, when you put on a gradient, you have different frequencies as a function in space. So the Larmor frequency is now a function of position in space. It's the default frequency plus this r dot g. In the x direction, it's a little easier to think of. You've got the on resonance frequency plus x times gx. So the frequency is encoded in position. So when you have that gradient on. And if you record that for a certain period, for a period of time, like you leave the gradient on and you want to integrate what is the effect of having a different frequency, you can accumulate phase. And so then you'd be integrating over time here. And if you do this, if you put a gradient on for a certain period of time, the phase accumulated is a function of position. And these equations are really the basis of the frequency and phase encoding that we'll talk about next. Okay, that's the end of the slide. I'm going to pick up on the slide for the end.